So hi everyone, I'm Jiaqing. I'm currently a postdoc at Siemens Institute at UC Berkeley. So today we were talking about our recent work on predicting properties of quantum thermostats from a single trajectory. So this is a joint work with Jiaqing and Ning from Berkeley. And our paper will be archived soon. So to begin with, I should first introduce the key task in this talk. So as many people already mentioned in the previous talks, the key concept in this talk will also be thermostats, which describe many-body system at finite temperature. So intuitively, those thermostats are just some mass model to describe like molecules of materials at finite temperature. More precisely, this concept also has been introduced many times in previous work, which is so more precisely, thermostats have parameters. One is called inverse temperature, which is beta, which is a scalar, equals to 1 over the temperature. And another parameter is a matrix H, which is called local Hamiltonian. So local Hamiltonian, just a model to describe molecules. For different molecules, you have different H. But anyway, so the Gibbs states at inverse temperature beta and the local Hamiltonian H is defined as an exponential function divided the normalization constant. So in other words, Gibbs states is a distribution over eigenstates. So this is a very popular concept in this workshop. So the key task in this talk, yesterday, there are a lot of works introducing how to prepare this Gibbs states. So in this talk, we're focusing on a further task. It's like we are trying to predict or estimate properties of thermostats, which just compute the observable values. Okay, so this is our task. So before I proceed, I also want to mention some other related area. So from the introduction, you may already see, the problems of estimating properties of thermostats is directly related to computational chemistry or physics. But in case you are from computer science or math, I also want to mention a related area, which is a separate area in machine learning. So what do I mean? So if you ever heard of Boltzmann machine, they use in Boltzmann machine they use Gibbs states as a generative model to model distribution, and for both quantum and classical Boltzmann machine, our task, which aims to estimate the observable value, will correspond to computing the gradient of Boltzmann machine. So this is some related area. Okay, so this is our key task. So before I start to talking about what we were doing, I wish to briefly mention some existing method. So to begin with, I think it might be important to slightly mention the classical algorithm. So the thing I want to explain is the task of estimating thermal expectation value. Is a very fundamental and old topic in computational chemistry. So over the last decade, there are already a lot of classical algorithms, and among them, one of the most popular ones is the Monte Carlo method. There are a lot of variants, including molecular dynamic simulation and machine testing. But the details is not important. I just want to justify those methods. Although they achieve great success in many areas, but they face some problem for general Hamiltonian. So in other words, they have limited accuracy for general quantum, especially strongly interacting systems like superconductor or catalyst. So that's why we were interested in developing quantum algorithm for this problem. So yeah, as I said, the key focus in this talk will be a quantum approach for tackle this problem. Before our work, most existing work are working on quantum Gibbs sampling, which is a quantum analog of MCMC algorithm. So the advantage of quantum Gibbs sampling is there's no sign problem because you are just using quantum system to simulate quantum system, and this indicates this might be a promising approach to achieving high accuracy for general quantum system. So the common goal of quantum Gibbs sampling, as already mentioned many times, is like you want to design a quantum channel which can drive any initial state to the Gibbs state. And as mentioned in like Evan's talk previously, like one of the key quantity you care about in Gibbs sampling is the mixing time, which is roughly speaking the time you need to drive any initial state to the Gibbs state. So I mean, so over the last few years, there already been a lot of progress in designing quantum Gibbs samplers, and I think yesterday yesterday the speakers give a lot of introductions on the details of those algorithms. So for this talk, like the details of this algorithm are not important. So all I want to know at this page is like there exists quantum Gibbs sampling algorithm. So the focus of this talk is slightly different. So the focus of this talk is like we want to use quantum Gibbs sampling algorithm as a subroutine to estimate observable value. So I may want to pause here for a little bit because at this point you might feel a bit confused. You might think like, okay, what she's talking about, like, isn't this a trivial task? Like once I have a Gibbs sampling algorithm, like why can't I just prepare the Gibbs state and measure, right? So if you are thinking about this, I think you have critical thinking. So I mean, like, you're right. There exists straightforward method, but the key information I want to give in this talk is like the straightforward method is not necessarily the best, and we claim there is room to do better. Any question here? Okay, so for simplicity, like in the following, we will mainly focusing on like computing the average energy. So we are focusing on take O to be H. So we could generalize our method to any observable which can be measured by a detailed balance channel. And we also have some idea for general observables, but let's delay the discussion later. And then let's currently focusing on computing trace H to the beta. So the following talk will be organized as follows. So first we will talk about the straightforward approach, and then we will talk about our approach, which can be summarized as a single trajectory approach. And after that, I will talk about the challenge and strategies, like why this result is not directly get from the classical results. And I think, and then there's also another thing important to mention is like there are some practical mode. What you need to do if you don't know like any prior knowledge. So that's the outline. Okay, feel free to stop me if you have questions. So let's begin with a multi-trajectory approach. So recall that our goal is to, we focus on tracing, calculate the average energy, trace H to the beta H, and we assume we have Gibbs sampling algorithm which can drive any initial state to Gibbs state in a mixing time. So when you have, as I mentioned before, like when you have a Gibbs sampling algorithm, the most straightforward approach to estimate the observable value is just run multiple independent trajectory. So you run mixing time, you run a lot of trajectory, you get a lot of samples of the beta H, then you measure, and you get get a good estimate of trace H to the beta H. And according to standard theory, if you want to get a desired thing, you need to run like this. You need to run like n numbers of like trajectories. So prepare n numbers of copies. So the number of n is not that important in this talk, but I just want to mention like I use this n as a number of trajectories. So the key thing I want to mention is in fact the key quantity considered in this talk is the total inversion time. So for example, for the multi-trajectory approach, the total Gibbs sampling time is n times t mix, because for each sample you pay t mix to get the sample, and the key result or the key thing we claim is like to get the same precision. In fact, you can reduce you can use like shorter keep sampling time. And if you only want to remember one sentence from this talk, I would say like we claim it's possible to get effectively independent sample with a time scale shorter than t-mix. So like, I mean, a rough understanding of like the multi-trajectory approach is like you spend mixing time to get pair sample. And what we claim is like it's possible to get pair sample with a time shorter than t-mix. And this is how we, reduce the total running time. Any question on our goal? Okay. So this is our claim. And you may ask, okay, then what's the method? So one of the most important slides is this slide. So I'm going to explain the algorithm. So the algorithm we use is called, can be described as single trajectory approach. So this is in fact also used in like classical literature. Although later I will explain why, what's the non-trivial part in the quantum case. But before that, let me just first explain what's this algorithm. So what's a single trajectory approach? So in this method, like you run Gibbs sampling, but you divide the Gibbs sampling process into two stages. The first stage is called burn-in. In this stage, what you are doing is like, you begin from an arbitrary initial state, and run a time scale like similar to t-mix, such that to ensure the current tends close to the Gibbs state. So the purpose of this burn-in stage, is try to eliminate the bias in this sample. So for example, if I measure at this point, if I measure at the end of the burn-in stage, I get a sample, and although it might not be precise, but at least it's unbiased. So that's the purpose of the burn-in stage. And after the burn-in stage, you will enter a sampling stage, which basically means like you, keep going, keep sampling, but you start taking samples. So more precisely, in the sampling stage, you perform measurement after every fixed time evolution. So recall that in the multiple trajectory approach, you can interpret as you perform measurement after every mixing time. And compared to that, in the single trajectory approach, you're performing measurement after every fixed time. So for example, if you are running like Nibeladian dynamics, you could choose to take measurement after every 1 times L. This one is just an arbitrary number you choose. And another thing I should emphasize or I should mention is so in this picture, you're not doing an arbitrary measurement. So you need to do some measurement which is coherent. So for example, it's not something very complicated. It's just some kind. So for the operator H, what you were doing is just some kind of QPE, quantum phase estimation. But of course, you might think of, quantum phase estimation is very expensive. But we will show the expensive version is not necessary. You can do something only incurs logarithmic overhead. So which is a special version of quantum phase estimation. But in summary, this algorithm is you first run a burn-in stage, then you run a sampling stage where you keep going, you keep doing keep sampling, but you take measurement after every fixed time. So for notation purpose, here I use E1 and ET I use ET to represent the measurement outcome of the T's measurement. And in this method, the estimation of the target value is estimated by the empiric average, which is just something you can calculate along the trajectory. Question?
So after each measurement, you don't do anything to try to reset the state. You just wait for it to hopefully thermalize again faster than t-mix.
Yes, exactly. So I think that's a very good question because that somehow, is one of the reasons why this works better. I will explain later more. Any more question about the product itself? Okay, so this is just an algorithm. I mean, like, the key thing is how about its performance? It's like why this is good or not. I mean, how quickly this empiric average converge to the target value. So I mean, intuitively, like so if you're looking at this empiric average, the first thing you might notice, like I mean, U1 and U2, the really sequential samples are not independent because you only involve like the Gibbs sampling for constant time, and to make sure, I mean, this empiric average, I mean, give a precise like estimation. The key quantity you care about is, I mean, how quickly those sample becomes independent, like how many effective independent samples you are getting from this trajectory. So like in the following, I will mainly focusing on explaining like this, I mean, how quickly the samples becomes effectively independent from the start point. So the key concepts in this like analysis or in this framework is called autocorrelation time. So like intuitively speaking, autocorrelation time, I mean, is the time scale which categorize, I mean, how quickly U1 and ET becomes effectively independent. So recall that our method is like, I mean, run a Markov chain for mixing time, and then like keep doing like coherent measurement, such that, I mean, in the sampling stage, at every point, if you're looking at the chain, it's in the Gibbs state. Although it's a different concept from like the correlation along this trajectory. The key thing, I mean, you might want to remember is like, I mean, how, like, you want to remember is like effective independent samples I get every autocorrelation time. So there is a formula for autocorrelation time, which is roughly the sum of the correlation from current from now to future, like normalized by variance. So like it might take some time to understand this formula, but we will not use the formula later. So like it's just something that it just exists. The thing I might want to explain is like, I mean, how does this autocorrelation time connect to the performance of the empiric sum? So in fact, this is nothing like too fancy. Like it's not fancy. It's just connected by the performance of empiric average by using Chebyshev inequality. So in other words, I'm saying like the effective independence is characterized up to second moment. Sorry, any question?
What's the var h again?
Variance H?
Yeah.
Yeah, it's a observable variance. It's like you measure the beta H, you measure Gibbs state by H, the variance of this measurement. So this is the autocorrelation time. The thing you might want to keep in mind is like, I mean, you might ask yourself like, what's the key thing I'm claiming? So the key thing I'm trying to convince you is like in this picture, the total running time is shorter than the straightforward approach, and the key reason is because this autocorrelation time typically is much smaller than mixing time, which I will explain later in the next. But if you trust me, this is true, then this basically means like you can get effective independent sample with the time scale shorter than the mixing time. As a consequence, this implies, I mean, to get the same precision, for example, to get precision epsilon to the observable value, the total running time you need is mixing time plus n times autocorrelation time, because like that's a number of samples you need to take, which is much smaller than n times t mix, which is the total time you are using for multiple trajectory approach. Any question here?
Yeah, I think I might misunderstand it. So previously, I think after you do the measurement, then your current state get destroyed. Then you need to wait for a long time until it becomes. But it seems like so here your problem is not about your state get destroyed. It's just about whether the two so E1 and ET are not independent. Right?
I mean that's a very good question. So so the algorithm is still the same. You will keep doing measurements every constant time. What I'm saying is like the effective independent samples are getting every autocorrelation time, and the total running time is n times autocorrelation time. So,
But after you do the measurement,
yes,
then your state is no longer the thermal state.
that's true.
Right. So then, how do you guarantee that when you do the measurement at the next time, you still have some biased estimation?
I mean that's why you need to characterize the autocorrelation time. So like it's true like the consecutive samples are correlated.
I think he's asking about the bias.
Yeah.
Indeed, you also show bias is controlled.
Okay, I see. Yes,
Yeah.
that's my question. Thank you.
So like the measurement is coherent. So for all the for all the measurement taken on the orange line, it should be is guaranteed to be unbiased. Yeah, but the key thing you want to bound is the correlation. Any more questions? Do you have a question?
Actually, just a small question. So here the autocorrelation time would be something like equal to the thermalization time from special states?
Yeah, that's a perfect observation. That's next slide.
Okay.
Very good. Any more questions? Okay, so like as many audience already noticed, I mean the key thing you might want to understand is like, okay, why does this procedure helps? Like why autocorrelation time is shorter than the mixing time? So I have two slides for this. For this question, and each slide have several sub-slides, so there will be a lot of information. So feel free to stop me if you have any question. So okay, the first slide is about the intuitive reason, and later I will give a general bound. So first, I just want to recall that the autocorrelation time, the time scale for the samples to become effectively independent. So as many people many audience ask, why this autocorrelation can be shorter than the mixing time. So there are two intuitive reasons. The first one is warm start, is exactly Samuel audience mentioned. So what do I mean? In autocorrelation time, in the analysis of autocorrelation time in the sampling stage, which corresponds to orange line, at any point, the change is on Gibbs distribution, because we were performing coherent measurement. So what does this mean? This means in the analysis of autocorrelation time, the start point is always from the Gibbs distribution, which is different compared to the mixing time, where the start point is assumed to be the worst case. So let me draw you a graph to give you an intuitive understanding. So I'm going to talk about a toy example. It's not fancy, but so imagine you have Hamiltonian, which have eigenstates, states, and for some reason you might imagine this eigenstate is unaware. So here the size of the circle corresponds to the probability in the Gibbs state. So since we know Gibbs states favors states of low energy, so that's why I draw a big circle for the 0. So imagine if you unfortunately working with a Markov chain, which only allows transitions between eigenstates of similar energy. So for example, in some of the Markov chain, you restrict the energy you could transit. So in this case, the mixing time should be at least m, because this will be the time you need to traverse from a worst case, the phi point, to a point which has non-negligible probability. But however, so this is the case for auto-correction time, because it's the worst case time. So for mixing time. But the auto-correction time is a very different story. You may ask why. So as I mentioned, like the auto-correction time uses a warm start. So imagine like, in the sampling stage, we always guarantee the start point is from Gibbs distribution. And we know, so if the case is like, if this will satisfy like most of the probability in Gibbs distribution lies in the vanity, then like Gibbs state gives a warm start, because very likely you start from the vanity, and then the time to mix to Gibbs state again is just the time you need to traverse over the vanity. So that's the intuitive reason. So before question, let me give a slightly more concrete example. So a toy example might be like quantum burst exchange, which you might imagine as an oscillator of different energy level. So the dynamics considered can, roughly speaking, so this is something not very precise, but roughly speaking, you can view it as a biased random walk between eigenstates. So between nearby eigenstates. So in this case, the mixing time you can show is like m, because that's the worst case time traverse from the up button. But however, the auto-correction time is different, because in this case, in Gibbs distribution, it corresponds to a geometric series, and most of the probability just like in the button. So the auto-correction time will just correspond to start from button and mix over this place. Will be like independent of system size. So this is the first reason. Like, any more question here?
Yeah. So, but this argument seems to be really general, right? Are you saying MC is better than MC? Like, is this like auto-correlation time is smaller than mixing time is a general performance? Or what's the condition for this?
In fact, this is a standard method used in classical Gibbs sampling. Like in classical MC literature, it seems like people are not nobody use. Okay, I shouldn't claim nobody, but most people were using this approach rather than run for mixing time every time. So I think it's a very general thing.
The autocorrelation time, is that informed by your measurement outcomes, or do you take it to be the same regardless of the outcomes you get along the way?
You mean is the observer dependent?
Yeah, outcome dependent. If you, in the unlikely scenario that you get a very high energy, does that change how long you wait until you do the next measurement, or will that?
So yeah, I think definitely it will. So first, like the performance it will be like a probability is the average performance, right? So like when you even when you use multi-trajectory approach, the real result you get is like with what probability you get a epsilon precise thing. So as long as that probability is, so that in fact there are two regions. This is a very good question. There are two regions. One region is like that probability is negligible, that everything is fine. Another region is like that probability, is a small constant, but in practice, it's possible like for most cases you have a desired precision, right? So that's also fine.
So I'm wondering that we go back to the our last question. So to make sure that in each step your estimations is optimized, then do you need to make sure your observable compute with H?
What's your last sentence?
So do you need your observable commute with H?
That's one of the case, yeah.
That's one of the cases, and
Yeah.
also the other cases.
So like a short answer would be first, like this can be directly generalized to any observable which can be measured in a detailed balanced way. So this should be more general than commuting. And for even more general observable, you can use operator Fourier transform to make it closer to the commuting case, although this should be analyzed by case. I will mention later. Okay.
So Just to clarify, if you have two very deep basins and the autocorrelation time is still exponential?
That's next example. Great. So I think so that's a community story. That's exactly the next example. So the first, I'm explaining the intuitive reason. The first is warm start, and the second reason is because autocorrelation time is an observable dependent value. So when I say autocorrelation time characterize, how consecutive samples become effectively independent. This is operator related thing, right? So for example, if this observable only is local, then it's natural to expect the autocorrelation time should be shorter than mixing time, because what you need is just this Markov chain mixed locally on this region. And another example, possible case that autocorrelation time can be smaller than mixing time is when this problem has some, or when this observable has some symmetry. So I'm going to explain an example to explain this part. So it's not hard to come up with very artificial example to say, oh, they differ a lot. But if you want something slightly more natural, you may want to looking at the 2D EC model. So the low-term 2D EC model is exactly has two whales. So I'm not writing. I didn't write down the formula for this, but because I think I'm going to explain something more intuitive. So in this model, you can imagine, all the eigenstates lies in two whales, because in 2D EC model, you can somehow classify all the eigenstates into two phases. One is the first phase is the states which most of them are spin up, and the other phase is most of them are spin down. And the mixing time will be very large because the energy barrier is pretty high. It's if you want to translate from all spin down to all spin up, you need to go through an energy change of O(n) in a non-trivial way. This will cause classical results in classical literature shows mixing time is exponentially large. But however, the autocorrelation time is a different story. So I think in this literature for mixing in a phase could imply the autocorrelation time for energy might be polynomial. So let me give you the reasoning. So the reasoning is because so the key thing which might make this work because energy is symmetric. It's symmetric in the two whales. So to compute the energy, you don't really need to mix to the global thing. The only thing you need, because energy is symmetric on two whales, the only thing you need to do is mixing in the O(n) phase, which has been already proved by a lot of classical literature. Did I answer your question? Any more questions? Yeah. Okay, so those are two example intuitive reasons for bounding this kind of autocorrelation time. So for rigorous results, we can also get a bound for general Markov chain. So our result is similar to the classical literature, which says at least for the statement, which says in quantum Gibbs sampling, for any observable, which can be measured by detailed balance channel, the autocorrelation time is bounded by a viral gap. So the detailed balance channel is a very technical definition, but roughly speaking, as I mentioned before, the key thing we need is, the measurement does not change the Gibbs ensemble. So that's the key thing we need. If you want, very concrete example, the most concrete example is H itself, and any observer which commute with H. So for those things, you can do some kind of phase estimation, which can naturally lead to a detailed balanced channel. And for those observers, they already includes a lot of things which, is meaningful. And as I mentioned before, like like for more general observable, like we will discuss later if I have time. So, but for simplicity, like if you think all those things are too abstract, let's just looking at the edge.
What's the definition of a detailed balance observable?
Sorry, I mean observable which can be measured by a detailed balance channel. So I mean when you measure something, you define a channel, and for unobservable, there might be multiple ways to measure it. But I mean for edge, you can use some kinds of, for example, for edge, if you measure in anything basis, it satisfies detailed balance.
And what notion of detailed balance, KMS, GNS, does it matter?
For this proof, in fact doesn't matter. It works for any alpha. Yeah, both KMS and GNS. But for concrete thing, like I mean, to instantiate the quantitative sampling algorithm, we only know KMS one. Yeah. Okay, so that's a disturbance balance thing. Like the second thing I need to explain is, I mean, how does this gap compare to like mixing time? So I mean, short answer is like they, according to this bound, they can differ from like a system size. So mixing time is upper bounded by 1 over gap times log sigma man inverse, where sigma man is the smallest probability in Gibbs distribution, which should be exponentially small. When you take a log, it will be like something related to n. So as a conclusion, from a theory bound, like you can claim like the autocorrelation time can differ from mixing time by a factor of n. Although like the thing I want to emphasize is like this bound is very general. It works for any observable and any Markov chain. That's why you get a loose bound as one gap. But when you consider specific system, the separation can be much larger, as I explained in previous examples.
Can you remind me what is the definition of correlation time?
So it's almost like the sum over the correlation between current sample to the sample in the future.
But is that sufficient for estimating the observable? So is that sufficient?
Yeah. You can prove like for all the things I have.
Yeah, but in quantum case, you have the state will collapse after each measurement. So
Yeah. All the problem has already been considered. Yeah. I can explain offline.
So this detailed balance observable, like, what kind of observables is it? Like, is there a restriction to the types of observables you can like characterize?
Yeah, I mean the simplest one is anything which commute with edge, like including like energy, heat capacity, and you can also use those quantity to estimate partition function.
Right. So somehow like the integrals of motion somehow.
Yeah. That's the most natural thing, but in general, like you can easily construct observer which does not commute with edge, but still satisfy detailed balance. But the problem is like I don't know what's the physical quantity they correspond to.
Okay. Yes.
Okay.
Got it.
Is it possible that there is an efficient way of measuring the observable, but that does not detailed balance, and there's no efficient way of measuring in a detailed balance way? For example, with H, I would assume like measuring local terms, but then I get more information than just the energy. Is it still detailed balance if I do that, or do I have to do it in a smart way as well?
So like so for edge, you can like measuring local term doesn't work, but you need to do some kind of QPE. But the thing I want to claim is like the QPE we performed has very only increased logarithmic overhead compared to the simple measurement, which is next page. Great question. So so as they asked, there are something very important to explain. The first, I explain why our result is not trivial. Explain all the concerns about quantum Gibbs sampling for this topic. So the first thing is like measurement will disturb Gibbs sampling, and the second thing is like how to reduce the cost of QPE. So the first thing, as Hongyu mentioned, the measurement will disrupt the process. As the first coherent measurement doesn't change the Gibbs ensemble, but it does change the Gibbs sampling process. So more precisely, I mean, if we're looking at the classical literature, about looking at the classical Markov chain, you can compute the energy just by looking at the configuration, right? It doesn't change anything. It doesn't change the Markov chain process. You can keep going. But however, for quantum Gibbs sampling, this is different. So just suppose we were doing we were measuring H. So in quantum Gibbs sampling, everything is very entangled. If you begin from an eigenn state, after constant evolution, you will get a state which is a superposition over many eigenn states. And especially for the current Gibbs sampling algorithm, which has logarithmic dependence on precision, this intermediate state will be a state over energy of spanned by constant. So it's a highly entangled state. Then at this point, if you measure in the eigenn basis, for example, you measure H in the best way, in eigenn basis, you will collapse the intermediate state. And you did change the dynamics. And so more precisely, when you measure, you change the effective channel. So if we use N to represent the Gibbs sampling channel, and M represents the channel used in the measurement, then when you insert in measurement, the channel you are using is a new channel. It's different from N itself. So this potentially will influence the mixing time because you are using a different channel, as well as the autocorrelation time. The key thing we observe is this change it, but does not change it in a very bad way. At least when you insert in coherent measurement, it never decrease the gap. So the measurement, the mixing time doesn't increase. And the proof, once you get the key idea, the proof is not very hard for this part. You just compare the directional form and use contractivity properties. Oh, sorry, I should go back. I think I have. So this is the first reason why it's not trivial.
Can I ask a quick question? So here, although you show the gap does not decrease, you still need to use the starting condition to make sure you don't have that log and sigma inverse mean factor, right?
Yeah. Yeah, exactly. I use this to. The log sigma mine is something from the Gibbs state, which is fixed. Yeah. Okay, so this is the first reason why it's non-trivial. But for the algorithm, for understanding the algorithm, the second part is also very important because it influences how you choose measurement. So the second thing you should be very careful is about the cost of QPE. So to recall, we might want to first understand what's happening in classical case. So in classical Markov chain, as I said before, the single trajectory approach is a standard approach. The measurement or the cost of computing the energy is not for free, but it's fine, it's okay, it's acceptable. So for example, if you were doing 2D EC model to compute the energy of a current configuration, the gate cost will be O(n) because there are O(n) edges. And the depth can be O1 because you can parallelize it. So this is what happened in the classical case. But however, when you were doing quantum Gibbs sampling, and you try to do something as I claimed, you should be very, very careful. Because, quantum physics makes it expensive, as you may already know. It's expensive in the sense that about the precision. So if you want to get a high precision, like ipso precise QPE, you need to pay a huge overhead, which might potentially make this method just not as good as the straightforward method. So the key thing we notice is this is not necessary. You can do something better. So the key thing we notice is for our method, for our target, it's not necessary need to do high precision QPE. All you need is to do unbiased QPE. Why? So this is because in our method we already take a lot of samples along the trajectory. So you pay a cost of number of samples to reduce the bias. To reduce the bias in the samples to get precise thing. So this means for each individual measurement, it's not that important to measure to that precise. So so the conclusion is like you can construct a measurement, which is from some previous paper, by only increase the logarithmic overhead, which is something like this. It's like compared to the gate cost, which is n epsilon inverse, you only pay a cost of 0.0 log epsilon. So if you want to know slightly more details, it's just like a Gaussian filtered QPE, where the variance of this the precision of this QPE is a constant. I think I have 5 more minutes, right? Okay. So finally, I mean, like, there's one more thing I should mention. So for another advantage of, or like feature of our algorithm is like, you can run it in a practical setting without lowering the mixing time or alteration time. So when the place we use like the mixing time is like in the Berkeley stage. If you don't know the mixing time, what you were doing is just like, okay, you choose a fixed number. So this algorithm still works in the sense that the empirical average will still converge to the target value, although it will with a slower rate because you were taking some better sample in the beginning. So in practice, like what you can do is just like, you run this chain and collect the data along the trajectory. And you may choose to stop like when you think this start to converge. And if you are, worried about the metastability, you might want to run multiple chains and begin from different start points. And once they start converge together, maybe you think it's you can stop at that moment. So like the method I described is not invented by me. It's in fact some widely used method in the classical literature to like empirically verifying the convergence of classical Markov chain. So finally, I just want to briefly mention like the possible extension. So first, as I mentioned before, like our result, all the results I'm saying now can be directly, okay, it's not that direct, but it can be generalized to any observable which can be measured in a detailed balanced way. In the sense that we can prove the total time you need is mixing time plus n times autocorrelation time, and where the autocorrelation time is upper bounded by 1 over the gap. So this is the case which we can definitely work for. And the case we get some result, but not a definite result, is for the even more general case. So for more general observable, if you directly measure it, it cannot fix the Gibbs state. But however, it's possible to design another method to, satisfy fix the Gibbs states, and also from the measurement outcome, you can recover the measurement value. You may ask how. So this technique, in fact, is lies in the beginning of designing Gibbs sampling algorithm, which is operator for transform. So due to time limit, I won't talk about too much details. But roughly speaking, this technique allows you to transform an observable to another observable, such that the new observable is more commuting with edge. So roughly speaking, if you express O in the engine space of edge, this O hat tau is effectively, filtering out all the a lot of components which does not commute with edge. And more precisely, if you make tau to 0, this O hat tau will become more and more commute with edge. And the most importantly, the observed value of O hat tau equals to the observed value of the original Hamiltonian. So instead of measuring O, you can measure O hat tau. So there is a formula for, this operator for a transform. However, it's not important to explain at this moment. The key thing you might care about is how to implement this. So I just want to mention it's possible to implement the measurement for O hat tau by using Hamiltonian evolution of edge. And the cost will be mainly dominated by this tau. So intuitively, you need to choose tau to be very small to make it fix the Gibbs states. And so the implementation cost of OHA et al. Really depends on like how quickly this long shrinks, and the speed of this, the decay of this long depends on the spectrum property of the edge. So which is very hard to get like very rigorous result, except for some very special case. For example, you could show, you can take this tau to be logarithmic, if this system is gapped. Okay, so this is a case for general observables. So finally, we can conclude, go to a summary and open question 16. So summary is like what we're doing is like we design a single trajectory approach to reduce the sampling cost. And the key concept is the autocorrelation time. And we claim we get a substantial sampling reduction for any observable which can be measured in a detail balanced way, for example, like edge. So the open question is mainly about, is it possible to generalize our result to, more general observables? So as I mentioned before, like there is a technique which is operator Fourier transform. But although analyzing the performance needs to assume the make assumptions on the spectrum property of edge, which is not that elegant. So I personally feel it might be more effective to do numerous experiments to see how it behaves for system of interest. And besides that, in fact, although I didn't mention details, but I think it's still possible you can get rigorous results, but from another method. So recall that I said our method works for any observable which can be measured in a detail balanced way. So if you're looking at the details of those Gibbs sampling algorithm, you might realize a common feature of them or a common technique of them is, given any arbitrary observable, they could transform this observable to a channel which is detail balanced. So that they can do something like this. But the problem is what we are not sure is how does this new channel relates to the original observable value. That's something we are not sure. But I feel there might be some possible ways along those techniques. But finally, it's also possible that there will be a intrinsic distinction from observables, general observables and special observables. So it's possible that there will be some kinds of lower bound to stop you doing similar thing for general observables. That will also be an interesting direction. Okay, thanks for listening. Any questions?